Hey, Physics 1. I'm going to go through some examples involving waves in standing waves in different media. So standing waves on a string, standing waves in a column of air, standing waves in a closed-ended tube. And we're going to go through some examples where we're going to figure out how to solve problems like this. And one of the most important things you can do when you are trying to understand standing waves is to remember the importance of drawing the situation. Please do not try to memorize equations to represent, say, the length of the string or the wavelength of a standing wave. Draw the situation, make sure you understand what a node is and what an antinode is and why they occur and where they occur and the different types of standing waves that we can generate. And that's going to help you a lot more. That's going to be something that you can, weeks from now still remember how to do, or months from now still be able to do. So let me give you an example here. We have a string that is 1.5 meters long. And with this 1.5 meter long string, we're going to have it vibrating in the first harmonic. And when it's vibrating in the first harmonic, what we can observe is an oscillation of 33 complete vibrational cycles every 10 seconds. With that information, we're going to determine frequency, period, wavelength, and wave speed for this wave. So we've got a few pieces of information. We know our string length is 1.5 meters. We know it's in the first harmonic. The first harmonic is drawn as shown. For the first harmonic, for a standing wave on a string, remember I'm going to have a node at each end. And I'm not going to have any other nodes in the middle because we're going to make the longest possible wave we can have that generates a standing wave in the system, which means it has a node at either end. If I'm going to have a node at either end and basically no other repeats of that oscillation in between, then I'll have an antinode in the middle. That's half of a wave. From this information, I can look at this picture and say, well, that's only half of a wave that I've got standing in that system. So a full wave would look something like that. So if this were the full wavelength associated with this standing wave, would be that. And so the first thing I can check off here is I know for sure that the wavelength is going to equal 2 times the length of the string. So my wavelength in this case must be 3 meters. Okay, so I was looking for wavelength. All right, so wavelength I've got down. That's 3 meters. Let's see what else I can figure out. The other numerical information I have given is that there's 33 complete vibrational cycles in 10 seconds. So when we're talking about cycles per second, we're talking frequency. So in this case, my frequency should be the 33 cycles divided by 10 seconds. And I'll find then that my frequency in this case is 3.3 vibrations or cycles per second, which would be measured in hertz. Okay. So I know my frequency, I know my wavelength. The next thing, let's get out of the way, is period. What is the relationship between frequency and period? Well, frequency is cycles per second, and period is the number of seconds it takes for each cycle to occur, how long one cycle is. And so that means essentially that these are inverses of one another. Frequency is equal to 1 over the period of oscillation. So if I'm trying to solve for the period of oscillation, I'm going to need to take 1 divided by my frequency. And 1 divided by my frequency is going to be 1 divided by 3.3 hertz. And when you calculate that out, you should find that it's about 0.30. And that's inverse hertz. Well, hertz is inverse seconds, so inverse hertz, or period, must be measured in seconds. Let me write it up here. Period is 0.30 seconds. I have only one thing left to solve for. I need to find wave speed. Luckily, I have a nice handy equation that relates frequency and wavelength to wave speed. So if I want my wave speed, all I need to do is multiply my frequency, 3.3 hertz, multiplied by wavelength, 3 meters, and I'll find that that should be about 9.9. And looking at the units, I see I've got meters times hertz, but remember that hertz is just inverse seconds. So this is meters divided by seconds, which is good because that's typically the units I use to measure wave speed. All right, so we're done with that example. And again, notice that we start by looking at our picture. What information can we get from our picture? In this case, we use the information that was in the first harmonic to relate our length of the string to the wavelength of this wave. And then we use information about the relationship between frequency and period. Okay, so we use this equation right here. And then we also used our wave speed equation. Wave speed is frequency times wavelength. All right, we're going to do another one. And this one is also a problem involving a string that's producing a certain note, a certain pitch. And we're going to think about the waves on this string. The first thing it says is that we want to draw the situation. Well, if I'm drawing a wave on a string, then here's what I know for sure. I know that I have a node at one end and a node at the other. And if I want to find the string that's going to produce this, this note, I can assume that this is going to be resonating at our fundamental frequency. So let's draw it as if it were resonating at our fundamental frequency. In that case, I'm going to have this for my wave. This is our longest possible wavelength that can exist in this string. And so the length of the string, which is the thing that I'm trying to solve for, is given there. All right, and a couple other things I know. I know that the frequency of this wave is given at 512 hertz. I know the wave speed is 1040 meters per second. And I can look at this picture and also figure out the wavelength. Because the wavelength here should be equal to 2 times the length of the string. And now I'm getting to the point where I'm pretty close to being able to solve for the length of that string. Notice that I'm in the fundamental frequency. And so for our fundamental frequency, the wavelength associated with that is going to be the longest possible wavelength that can generate a standing wave in that string. And that's going to have a node at each of those ends. I would like to calculate the length of this string. Let's first calculate the wavelength of this wave using our equation that wave speed is equal to frequency times wavelength. Because if I want to find the wavelength then, all I need to do is take my wave speed, 1040 meters per second, and divide by my frequency, 512 hertz. And I should find that the wavelength of this wave is 2.03 meters. However, that's not the same as the length of this string. The string itself that we're oscillating on is much shorter. It's half the length of our wavelength for this standing wave. So our string length is in fact the wavelength over 2, which should be roughly 1.02 meters, keeping in mind that we're rounding here. All right, so our string length, 1.02 meters. And again, I had to start by drawing a picture and then deciding how to relate it to my equations. What's the wavelength and frequency for the second harmonic? Well, if I want to draw the second harmonic, let's think about what that would look like. I know I have a string, and if I have a standing wave on a string, I'm going to have a node at each end. I need to compress this wave a little bit, make it a shorter wavelength, a higher frequency that also generates a standing wave. When I have a wave on a string, I need to have a node at each end. So what I'll do is I will take a look at my fundamental frequency, and I'm going to add another half wavelength on there and compress it into our wave. So our second harmonic should look like this. All right, so for our second harmonic, one thing to note, the length of the string itself equals our wavelength. So if I want to know the wavelength for the second harmonic, It's actually equal to 1.02 meters, roughly. Again, I've approximated here. And if it's equal to 1.02 meters, I also can figure out my frequency for that second harmonic. There's two ways I can do this now. The way that I'm going to encourage you to do that is to take a look at our fundamental frequency, 512 hertz. You see, for every standing wave, every higher harmonic, we can take an integer multiple times our fundamental frequency to get our next highest standing wave. So if I want the second harmonic, I'm going to take 2 times 512 hertz. And I should find my frequency is 1024 hertz for my second harmonic. There's another way we can do this as well, because I also have an equation that relates wave speed, frequency, and wavelength. So another way I could do this would be to say that, well, I know the wave speed through this wave. How do I know? Because it's the same medium it was before. And wave speed is going to be dependent only on our medium. So if I know the wave speed is 1040 meters per second, that should equal the frequency times our wavelength, 1.02 meters. You'll find in this case that our frequency of that second harmonic is 1020 hertz when you use this method of calculation. But I don't want that to throw you off, because I got 1020 here and 1024 here. But notice that I don't really have 4 significant figures. Okay, so within rounding for the significant figures, the fact that we rounded our string length earlier means that these are really identical answers, 2 different ways to get to the same value. So one thing we can do is use our knowledge that our standing waves are, for standing waves, our higher order harmonics are always integer multiples of our fundamental frequency. Or I can use my knowledge that wave speed, wave frequency, and wavelength are all related to one another. All right, so that was a second example involving a standing wave on a string. The next situation I want to take a look at involves a standing wave in a closed-ended pipe. In this case, this organ pipe that's described in the question has a fundamental frequency that's oscillating at a frequency of 256 hertz. The pipe is closed at one end and the speed of sound in air is 340 meters per second. We're going to start by drawing the situation. So when we draw a closed-ended pipe, I generally tend to draw it like this so that I know that this is the closed end. And I've got an open end over here. When I have an open end of the pipe, I need to have an antinode at that end. And when I have the closed end, I can't have any oscillation of the molecules at this end of the pipe. They're bumping against a solid surface, so there must be a node there, must be minimal oscillation at that point. So generally, the way that I draw a standing wave in a pipe is with the amplitude of my wave representing the oscillation, the amount of wiggle each of the air molecules of that position is exhibiting. So at this end here on the left, I have a closed end, I should have a node. And at the opposite end, I should have an antinode. If I'm drawing the fundamental frequency, I'm drawing the longest possible standing wave that can exist in this pipe. The longest possible standing wave doesn't cross that center line at all. It has no additional nodes and antinodes. It only has one node and one antinode. And so this longest possible wave looks like that. That is my fundamental frequency of oscillation in this standing wave. So that's my picture. Our next goal is going to be able to indicate or calculate the length of the pipe. How long does this pipe organ need to be? Well, one thing we might want to figure out is how the wavelength of this wave relates to the length of the pipe. Notice that we haven't drawn one full wave oscillation. We've only drawn 1/4 of a wave. And so the relationship between the wavelength and the length of the organ pipe is this: that 1/4 of the wavelength is equal to the length of that organ pipe. If I can calculate the wavelength, then I can figure out the length of the pipe itself. So our equation we might use to try to figure out that wavelength is our wave speed equation. Wave speed is equal to frequency multiplied by wavelength. And I know the wave speed because this is sound in air, and I know the fundamental frequency of this of the wave in this pipe. So I know that wavelength is equal to wave speed divided by frequency. So I'm going to take 340 meters per second. I'm going to divide that by 256 hertz, and I'll find the wavelength for this pipe to be 1.3 meters. But keep in mind that 1.3 meters is not the length of the organ pipe itself. I need to cut that by 4, because remember that the length of the pipe is equal to 1/4 of our wavelength. So calculate that out, and you should find that the length of that pipe is 0.33 meters. All right. With that part done, we're going to go on to think about the next part here. What's the wavelength and frequency of the third harmonic? Notice we skipped a harmonic. I didn't ask you about the second harmonic. The second harmonic cannot exist in a closed-ended pipe. Our third harmonic is going to be 3 times the fundamental frequency. So one thing that I know about my frequency for this standing wave is it should be roughly 3 times 256. We're going to have a node at one end and an antinode at the other. When I have a standing wave and I'm looking at my third harmonic, I can think about the relationship between the wavelength and the total length of the tube. For our fundamental frequency, the length of the tube was 1/4 of the wavelength. In this case, our wave is going to be 3 times higher frequency and 1/3 of the wavelength. Our length of the tube should equal 3/4 of a wave. So when I draw this out, I'm going to have an additional node, an additional antinode in here. So let's see, I'll need another node and another antinode. And my wave is going to look something like this, my standing wave. Notice I've got 1/4 of a wave and then another 1/4 of a wave to get to a half. And then I have another 1/4 of a wave. I've got 3/4 of the wave, but not quite all of the wave to get back to my original position in that wave. Okay? Now, remember that I've already determined the length of this pipe to be 0.33 meters. And so my next step is going to be to determine the wavelength and frequency. So one way that we can do that is with this equation. So if I know the length of the tube itself, I can figure out the wavelength because I know wavelength should equal 4/3 times the length of the tube. And what I find there is that my wavelength is 0.44 meters. The next step, finding frequency. Well, I can use my V equals frequency times wavelength equation if I like. So in this case, my frequency is the wave speed divided by the wavelength. I've just calculated the wavelength. and I can take 340 meters per second, all divided by my wavelength, 0.44 meters, and I'll find that my frequency for that third harmonic, to go along with my wavelength of the third harmonic, should be roughly 770 hertz. And again, I found this using my equation that wave speed is frequency times wavelength. There may be some rounding that's occurred here. You can think about our significant figures that are present in this system. In my calculations I've done, I've definitely rounded things along the way. Now, I said back at the beginning that our fundamental frequency was 256 hertz. So another way to check this, so another calculation we could do is say that the frequency of the third harmonic is an integer multiple of our fundamental frequency. So if I'm looking for the for the third harmonic, that third harmonic is going to equal 3 times our fundamental frequency, 256 hertz, and that should be 768 hertz. So pretty close to what we calculated, and definitely if we're to round that, it's going to be basically the same number. All right, so that was 3 quick examples involving the standing waves in various systems. So we did standing waves on a string and standing waves in a closed-ended tube. Remember to draw the situation. Make sure you are comfortable drawing those pictures of standing waves. And then from there, we're using our relationship between the wave length and the length of the tube or length of the string. We're using the fact that our fundamental frequency can be used to find our higher order harmonics, or we're using our equation that wave speed is equal to frequency times wavelength. That's all I've got for you. Make sure you try some example problems, and good luck with the homework, Physics 1.